Okay, let's look at section 6.4. This section talks about strong principle of mathematical induction. So this is just a little extension of principle of mathematical induction. Right, so it goes like this. Right, so we want to prove that for all n, integer n, starting from m, p of n is true. Right, so first, since again it starts from m, so we have to check. So make sure that the p of m is true. Right, then when the next thing is we have to make sure that when p of m is true, and also p of m plus 1, and all the way to, say, p of k. Right? Then assuming all the statements up to k is true, then this implies that p of k plus 1 is true. Right? Then we can conclude that for all n, integer n, starting from m, that the statement p of n is true. Right? So let's look at an example. So in order to find, in order to show that the p of k plus 1, it's going to rely on maybe a multiple previous statements. So that's the biggest difference between the principle of mathematical induction and a strong principle of mathematical induction. All right, so let's look at this example. So you have a sequence of numbers. A1 is 1, A2 is 4, A3 is 9. So we can guess that the formula will probably be an equals n squared. Right? Then this sequence has this recursive definition. You can see that the an is defined as an minus 1 minus an minus 2 plus an minus 3 plus 2 times 2n minus 3. Right? So let's prove this. So we're going to use an induction. So it's a proof by induction. Right? First one, we have to do a base case. Right? Since this recursive definition depends on 3 previous terms, right? So I'm gonna do 3 base cases starting from 1. Right? So A1 is obviously 1, which is given, but you can view it as 1 squared. So it fits the form right here. So fits the definition here. The formula. Right? A2 is 4, but the 4 is 2 squared. Right? It fits the form. Right? A3 is 9, but the 9 is also 3 squared. Right? So these 3 base cases, so base cases or base steps, when n equals 1, and n equals 2, n equals 3, the formula works out just fine. Right? So second step is induction hypotheses. So we're going to assume, right, since we checked the 3 base cases or base steps, we can assume 3 induction hypotheses. So which is AK minus 2 is k minus 2 squared. And we can also assume AK minus 1 is a quantity k minus 1 squared. And also AK is k squared. Right? So this is induction hypotheses. Right? So it's n equals k minus 2, n equals k minus 1, and n equals k. Right? And the third step, right, we need to consider AK plus 1. So we want to show that AK plus 1 is quantity K plus 1 squared, right? So we can use this recursive relation, so it's going to be 1 before, so it's going to be AK minus AK minus 1 plus AK minus 2 plus, right, so it's 2 times, right, now n is K plus 1, so it's K plus 1 minus 3, right? So let's simplify this. AK, according to induction hypotheses, we know that the AK is K squared. So this is K squared minus AK minus 1 is quantity K minus 1 squared, right? AK minus 2 is quantity K minus 2 squared, right? Plus, right, so if you multiply this out, so that's going to be 4K, right? So that's going to be, let's see, 2, 2, then 4 minus 6, so it's negative 2, right? So if you multiply this out, you will see that maybe I'll go here, right? You have K squared, right, minus K squared minus, so it's a plus 2K plus 1, so it's minus 1. I'm distributing the negative sign, plus K squared minus 4K plus 4 plus 4K minus 2, right? So we can see that there's x and negative K squared and there's positive K squared. And then you have a negative 4K and a positive 4K. So what's left is you have K squared. There's positive 2K. Right, then you have negative 1, positive 4, negative 2. So that's positive 1. Right, which is K plus 1 squared exactly, right? So this checks out, right? So therefore, so this was induction step where we're showing that n equals K plus 1. The formula still works out. So the last line is, therefore, for all natural number n, the formula for a sub n is n squared. Right? That's it. I hope that this was clear.